Hi, this is TheoryStation. I'm John Duggan. This is the Rational Choice Modeling Program. The series we're in is Individual and Social Choice, and this is installment 11 in the series. The last installment was a big one, doing most of the work for the proof of arrows theorem, but we cut it short because it was just going so long. So in this installment, we're just going back to the proof. So this is the proof of arrows theorem continued. And where we were was, well, there was quite a bit of setup. And then we said, okay, let's take a social preference function that satisfies the three axioms: rationality, IAA, and Pareto. And we said, well, we need to show that there's a dictator. So we really just need to show that there is a singleton decisive group. So we started a big proof by contradiction and we said, suppose there's not a singleton decisive group. So we had this little branching diagram, and we're going down that bottom branch, and we're going to show that the bottom branch actually can't obtain, and so we can cross it off. Right, so we're going to find a contradiction. We're doing this by a sequence of claims. What we did was we said, so suppose so we suppose that there is no singleton decisive group. So we said, well, let's just take the smallest decisive group we can that has more than one person, so we can break it up into two groups. Those groups are not decisive. In particular, if we call them G1 and G2, that means there's some A and B that G1 is not decisive for. It's not decisive for A over B. And we've been just tracing the implications of that. And so far, we've done two claims, which are reproduced here. So we've shown that there are not alternatives, X, Y, and Z, with this chain of decisiveness for the two groups, okay? G1 and G2 are not decisive, but they could be decisive for some alternatives over some others. It's just that they can't, those decisiveness conditions can't form a chain like this, okay? Claim 2 said, well, because G1 is not decisive for A over B, it turns out that the G2 is decisive for B over any third alternative X, okay? All right, we're going to use the logic of that claim. I should point out now that here we're framing claim 2 in terms of A, B, and a third alternative X. But whenever, if there's any, let's say, alternative C and D such that G1 is not decisive for C over D, we can use the same argument to show that for any third alternative, we have G2 decisive for C over that alternative. Okay, so I'm going to use, I've stated claim 2 in a specific way, but really the argument, the logic behind it is more general, and it applies whenever G1 is not decisive for one alternative over another. Okay, so let's move on to claim 3. Okay, claim 3 is that G2 is decisive for A over B. Okay, now how am I going to prove this? Well, I'm going to use the previous claims. Remember, in the one of the assumptions of Arrow's theorem was that there are at least 3 alternatives. So here I have a claim about A and B, but I know there's at least one other alternative out there. So let's pick one of those alternatives. Call it C. Right, so C is a third alternative. Okay. Now, we know from claim 2 right, claim 2 said that that G2 is decisive for B over any third alternative. So here's C, right? That's a third alternative. So claim 2 directly implies that G2 is decisive for B over C. Okay. Now, notice that we can't have G1 being decisive for C over A because that would give us a chain where B is decisive, sorry, G2 is decisive for B over C, G1 is decisive for C over A, but right, claim 1 says that you can't have a chain like that, right? So all right, so we can't have G1 being decisive for C over A. All right, well, okay, but now we can use the logic for claim 2, all right? By the argument for claim 2, right? Since we have, it's not the case that G1 is decisive for C over A, right? Notice the comparison to claim 2. This means that for any third alternative, x not equal to, well, here I'm talking about A and C. Okay. We have G2 is decisive for, now instead of B, I'm talking about A. Okay. In particular, so we can set, here we can set this x equal to B. And that gives us G2 is decisive for A over B, which is what we wanted to show. Okay, so so claim 3, given the other claims, is actually pretty straightforward. We don't have to construct any more profiles. Okay, and it's, you know, just using, we're kind of, as I said, we're exporting claim 2. Claim 2 was stated for particular alternatives, and here we're talking about A and C instead, but the logic still holds. All right. So now for claim 4, this is the last claim. We'll say that for any alternative not equal to A and B, G2 is decisive for X over A. All right. So for this, let's consider any third alternative, right? Any x. Okay, notice that we can't have G1 being decisive for B over X for then we would have we already showed G2 was decisive for A over B. If G1 were decisive for B over X, we would have this kind of chain of decisiveness that was ruled out in claim 1. Okay, so that tells us that it's not the case that G1 is decisive for B over X. All right, and now we're going to use the logic for claim 2 again. All right, and it follows that that G2 will be decisive for X over any third alternative not equal to B or X. In particular, we can think about A. A is a third alternative not equal to B or X, right? So that gives us this. That's what we wanted to claim. All right, so those are the 4 claims. The first 2 are the most complicated because we have to, think about preference profiles. Claims 3 and 4 just kind of build on the first 2 claims. And with those claims done, we're ready to see that, all right, this does not all hold up, okay? So the way I want to illustrate this is to construct a graph. We have alternatives A and B, and then we have all these other alternatives. There's at least one, but, all right, so we'll just do a blob for those other ones. Now, I'm going to construct the, I'm not going to depict the whole thing, but I'll show you part of the decisiveness relation for G2. Okay. So by our claims, so first of all, by claim 2, we've shown, and let me just do this in blue, we've shown that for any third alternative, G2 is decisive for B over that alternative, right? So there's an arc going from B to all these other alternatives. Claim 3 showed that G2 is decisive for A over B. And claim 4 shows that G2 is decisive for all these other alternatives over A. Okay. All right. So, we've actually seen, well, all right, so G2 actually is a group that has a lot of power. Now, now what I want to do is I want to think about G1. We haven't talked too much about G1 for a while, okay? Remember G1, it's in a symmetric situation to G2. So I can, anything I can prove for G1, or G2, I can prove for G1, vice versa. Now let's think about what the decisiveness relation for G1 looks like. In particular, I want to see where it can't have arcs, okay? So let me put that here. So the decisiveness relation for G1 cannot have the red arcs. Okay. Well, let me let's first think about this arc here, going from A to B. If there were if G1 were decisive for A over B, that would conflict with our claim 1, right? Because then we would have, if we take a different, a third alternative here, let's say C, G2 would be decisive for C over A, but then we would have G1 being decisive for A over B, and we'd have this chain of decisiveness that was ruled out in claim 1. So G1 cannot be decisive for A over B. So I'm going to put a red arc there to denote it can't be decisive for A over B. Also, it can't be decisive for B over A because precisely because G2 is decisive for A over B. Right? We can't have G1 decisive for A over B and G2 decisive for B over A. Then they would have, their power would come into conflict if you had a profile like this. Suppose you have a profile like, here where G1, put those guys first. They all prefer A to B. The guys in G2 prefer B to A. I don't care about the other guys, right? If the decisiveness arcs of G1 and G2 went in opposite directions between A and B, we would have a problem for this profile, right? Because, G1's decisive for A over B. So that means they get their way, right? Everyone in G1 prefers A to B. So the social preference is for A over B. But the same thing applies to G2 here. If G2 is decisive for B over A and they all prefer B to A, then they get their way. Those two things can't simultaneously hold. So we can't have, where are we? So the decisiveness relation for G1 can't have any arc. It can't have an arc going from A to B, and it can't have an arc going from B to A. Well, we can do that for these other ones as well. The same argument tells you, well, the decisiveness relation for G1 can't have an arc going from B to any of those other alternatives, because then that would give us a chain, right? So G2 would be decisive for A over B, but then G1 would be decisive for B over a third alternative. We'd have a chain. That can't happen. We also can't have an arc going against the blue arc. We also, just following this logic, we can't have the decisiveness relation for G1 can't have any arcs going from C to A, and it can't have anything going against the blue arc. Okay. As well, there can't be any arcs between these other alternatives, okay? Okay, because, if we had any arc between, like let's say, it's getting a little crowded there. All right, so let me draw this again. I had A and B and these other alternatives here. Okay, suppose that there was some alternative in here like C and then another alternative D, and suppose that G1 were decisive for C over D, okay? Well, but we know that well, you know, there's all these arcs too. Right. We've established that G2 is decisive for A over all these other alternatives. In particular, we have G2 decisive for A over C. If we had G1 being decisive for C over D, once again, we would conflict with claim 1. Okay, claim 1 turns out to be a very powerful claim with lots of implications. So what we see is that the decisiveness relation for G1 can't have any arcs between these other alternatives. It can't have any arcs going with the blue arcs or against them. Okay. The punchline here is that G1 can't have any arcs. We've just shown that. Okay. So with these 4 claims, we've gotten to the point here of, wow, so G1 is not decisive for any alternative over any other. And the contradiction where we finally get to is when we compare G1 and G2. These same arguments show us that G1, just like G2, has to be decisive for lots of things over lots of others. Okay. Right, but we just showed that it can't be decisive between any pair of alternatives. Okay. But the same argument with G1 and G2 switched implies that the decisiveness relation for G1 contains lots of arcs. I'm not going to be precise about lots, but it contains at least one. This is a contradiction. The decisiveness relation for G1 can't contain no arcs and also contain at least one arc. This contradiction establishes that smallest decisive group has one element. It consists of one individual. Okay. That individual is a dictator. That's one version of the proof of Arrow's theorem. There's lots of different proofs out there. This one, to my mind, is fairly simple because we only have to construct 2 preference profiles. Even so, the first time you see this, it's probably going to be a little bit dizzying, I suppose. But anyway, that's Arrow's theorem. It shows that these 3 ostensibly reasonable axioms, certainly desirable ones, they imply this concentration of power into a single individual. So obviously, there's no way of having those 3 axioms while still having a voting rule that's fair and doesn't give all power to one person. So that's the impossibility part, the impossibility result. And where it leaves us is just thinking about preference aggregation in a different way. So there really is not going to be one way of doing it that's the right way. You know, we can't even satisfy these three axioms. So we're not going to be able to find the perfect rule for aggregating preferences. Rather, what we find are, you know, some rules possess certain properties that are nice and some that are not so nice. We can certainly, you know, push things though, because the literature didn't just stop with Arrow's theorem. You know, one thing you might consider doing is relaxing some of the axioms. You know, rationality is a very strong axiom. IIA is a strong axiom. These can be relaxed. As well, we are, you know, we're using the assumption that the social preference function is defined over all possible preference profiles. And I mean, I used that in claims 1 and 2 in the proofs of those. You know, there are some situations where we're thinking about aggregating preferences where there is a lot of structure on the problem, and we can probably rule out some kinds of individual preferences or some profiles. Those are called restricted preference domains, and there things can become much more interesting. You can have possibility results. We'll see a little bit of that when we do, well, I'll do a series on the one-dimensional policy choice model. So I think that's enough on Arrow for now. So I'll let you digest that, and yeah, I hope it was at least interesting enough to take another look at to see if it makes sense when the dust settles. Anyway, I'll stop talking. That's the end of this series. The next one I plan to do is on this one-dimensional model, and you know, hopefully I'll see you there.